good afternoon or morning from wherever you're joining. Welcome to this webinar. Today's topic, Drive Till You Survive, Fundamentals of Off-Road Hydrogen. That's Digital Twin, hosted by Meyer HGT. My name is Adam Martin, and I'm going to be your host, and I'm going to do some of the presentation and be involved in some of the Q&A today. As we can't meet in person, a little background about myself. So I've spent a career in simulation and design exploration. A few kind of interesting facts about me and my interest you can see on the screen. Quite enjoy building radio-controlled aircraft, and spend a lot of time walking my dog, which is when I'm not working. I work for and really enjoy working for a company called Meyer HGT, and we're a worldwide Siemens partner, and we sell the majority of the simulation portfolio, as well as the obviously NX CAD and CAD/CAM authoring tools as a partner to Siemens. We've got staff worldwide, and a nice extra dimension is that Meyer started in the space industry, and we have authored many of the modules in the Siemens suite, particularly around the thermal flow aspects. So we're very familiar as a company, got a lot of very skilled engineers in multi-physics in those spaces, in that space. Today I'm excited to have join us Darius Perot, who's going to share some of his experiences building digital twins with system modeling tool AimSim, etc. So Darius, would you like to introduce yourself and
yes,
share a little background?
Can you hear me?
I can, yes.
Super. So as Adam said, my name is Darius Perot, and I'm an independent model-based systems engineering consultant. I've been using simulations for the last 13, almost 14 years, and my simulation job started with MESIM, and then I moved towards other and integrated other tools. And I was using those tools for simulations of different systems for off-highway machinery, construction equipment, and agricultural machinery. And it included, but wasn't limited to, hydraulics, mechanics, drive lines, different type of drive lines, starting with standard engine powered through the torque converter transmissions, access to wheels, going through hybrids to electric drivelines powered by batteries or fuel cells. I also developed some control algorithms and mainly put them on prototype machinery, so not for production code, but for prototypes. And I also was responsible for developing real-time digital twins for the machinery. So there are contact details on the slide, as you see. If you want to get in touch, please do not hesitate to do so.
Thank you, Darius. And yeah, we work together, and we're hoping today to share some interesting insights into how to do systems engineering and simulation, and in particular around fuel cells, which is quite a kind of new area. And Darius is going to share some of his experience in that space. So today's agenda looks a little like this. So I will cover a kind of quick introduction to a system simulation and AimSim, the tool that you'll see quite a lot of in this presentation. And then Darius will take us through some interesting background on hydrogen fuel cells and that technology, and the engineering aspects and challenges, and then how that was, some experience he's had building out digital twins of fuel cell based wheel loader. And then sort of towards the end, we'll wrap up with some practical steps on how you could potentially start these processes or take some of this and apply it to your products and your engineering processes. And then we'll have some time for QA at the end. So the first couple of minutes, I just wanted to give you an overview for those who not so maybe so familiar with system simulation and tools in that space. But just out of interest, we thought we'd just start with a question about sort of where your company is in this space, and do you use system simulation tools today, or is it something you're looking at? So I'm just about to launch a quick poll. The questions are fairly easy. The question's fairly easy. So does your company currently use system simulation to develop any products? Couple of answers: not currently, informal use. Maybe you've got one or two advanced users, or you've got a team. You know, so a lot of companies have dedicated teams for this now. So yeah, I can see some results coming in. Thank you very much for voting. All right. Okay, I'm going to close the poll there. All right. So I assume you can see the results now. So shared the results. So what I can see is so it's an interesting mix. So a fair few of you are currently not using, you know, and I assume you're probably looking as you've joined this session. Then there's some informal use, and then there's so some of the attendees obviously are probably part of those simulation teams within the company. So I will spend a little time, like I say, just giving you a bit of background on system simulation, and in particular a tool that we use, which is AimSim. So, okay, let's hide those results. Hopefully you can see my screen again, so we'll continue on. So just a quick overview of the tool that you'll see a fair bit of during this session, which is called software tool called AimSim. And we use this for the system simulation. Next, I'll show you a sort of practical example of the usage. This is just meant as an introduction to the whole idea, key concepts around system simulation and the type of tools involved. So AimSim is a tool we're talking about, and you'll see a lot in this presentation of these type of diagrams. Basically, what it allows you to do is build up system models of your system. And here we're primarily focused maybe on the mechatronic aspects of it. So you can see some things you might recognize, so a ram here for a hydraulic system or a valve. And as part of the tool, we have a whole group of libraries available from different area spaces. So you can see this: hydraulics, pneumatics, and we'll show a fair few examples of this as we go through the presentation. And what you can use this for, obviously, is to build up a system, model of your system. So it can be done as a small number of components or an entire vehicle. And then there's a lot of things you can then start doing with that in terms of developing a product. So you can do system sizing, and again, I'll cover some of that in the next few slides. You can look at controls validation, and we'll see how you can also link this into, say, hardware in the loop, software in the loop, etc. So that's what the AimSim tool is, and this is what is a lot of the diagrams you'll see in this presentation are based on and built with. So let's just get into a kind of practical example. I'm not going to go right into the detail. There is lots of detail in this example that you could go to. In fact, there's a web link here if you're interested in learning more about this particular example. But I just wanted to use this story to convey to you some of the things you can do with the AimSim tool and system simulation in general to set the context for some of the stuff Darius is going to show us when he gets into building a digital twin. So I guess one of the questions you might think is, well, why would you do this in the first place? So some of the things that come to mind in this particular example would be, you know, clearly we're trying to reduce emissions. So we're taking, you know, vehicles like this, electrifying them, so we reduce emissions, and there's a lot of regulations out there that are driving that in the industry. Another aspect of this is to stay ahead of the competition. So, you know, building more efficient, cleaner vehicles, something everyone wants to do. So this is a tool and a methodology that can help you to do that very efficiently without, you know, building lots of prototypes, doing lots of testing. You can use the system models to gain a lot of information at the beginning of the design process. So with that in mind, I've just outlined a couple of the challenges you might have if you set out on this kind of path to say, okay, let's take an existing vehicle design and try to figure out how we could make it zero emissions, maybe battery motor driven electric vehicle. So what you see on the screen is an AimSim system simulation model with the different components that make up our excavator. And what we're going to try and do with this, what we might use this for, is to firstly identify effectively the power requirements of our system, so that then we could figure out what we need in terms of electric motor power, electric motor and battery power, sorry, and then if we plug that system in, will it provide the enough energy and power to operate our vehicle in the way that we need it to. So this is a pre-built system model, just highlighting a couple of things in here. So again, you'll see a lot of these diagrams in this presentation, but you could probably recognize that this part of the system model represents the current engine in this system and the powertrain, and a lot of the powertrain components are shown in green here. And then this block in the middle, if you look, you can see the different hydraulic rams which are connected to a physical model of the boom, and it's modeling the movement of that boom with the input from the different rams. And we've got a hydraulic pump here which is feeding these valve assemblies to control that. There's also some extra bits down here around swinging around the boom arm. So that's all of the logic in terms of the control logic and the multi-physics equations representing how this vehicle is going to behave is captured behind this diagram. So what does this look like when you're actually doing systems modeling in a tool like AimSim? So short video here, just to again set the scene on how this stuff works. So I've kind of given you a quick overview of kind of what you're seeing visually. So if you're in the AimSim tool, we'd start with a model. And remember, our first objective here is really to figure out what's the energy requirement for our excavator if we were going to replace that engine system with a motor and a equivalent battery. So one of the things you can do with the AimSim tool straight out is model the 3D mechanical characteristics. So just to help explain what's going on here, this simulation is driven from the simulation model we've just seen. And we just use a simple 3D representation just to see what's going on. And this is stuff you can kind of do with AimSim. So that is kind of a drive cycle that we're running through this model. And as a result of running that drive cycle, we can now interrogate the model, as you can see on the screen here now, to see maybe the positions of the different hydraulic rams in the excavator design at a particular time. And then something quite useful we could get out of this is an understanding of the cycle time for that particular load cycle we were looking at. So how quickly does our current excavator run through that cycle time with its current power ratings, etc. Another area we could look at is, all right, so what is the responsiveness of the system based on the power available and the reaction of the excavator arm to those input commands, and the resulting load on the hydraulic pump, for example. So we can see how you could model that with a systems model. Here we get to kind of our challenge is understanding, okay, for that duty cycle that we've just seen, how much power is required to deliver that, and we can see the accumulation of energy requirement there. And you can imagine how that then can start saying, well, we know this now, we can start using this information to size up electric drive and possible battery requirements if we were going to make this a electric solution rather than engine driven. So another thing we can look at is where that energy is being used, and we can look at a breakdown of the energy losses in the different components in our excavator model. So yeah, just again illustrating to you some of the kind of practical uses of a system simulation model. And finally, I think this final plot, we just see the total energy consumed by the system. And again, that we can then use to feed into our further design steps along with the cycle time here. So hopefully that gives you a little sense of sort of what these systems models are and the kind of things you can start doing with them. So if we move to the next slide here. So just recap there, we saw how we could build out a systems model, look at the energy requirements and cycle time. Just to add, and this will come in important further on in the presentation, you can also look at things like the interaction of the bucket with a soil model, and it's possible to do some of that in AimSim. And Darius will show how we can take this even further into 3D models and into real-time models as well. But you can start out with everything at this kind of more, I guess, simpler level within the system model. A few other steps here. Just looking at my time, I'll keep moving forward here. So electric components need then to be chosen to meet those power and timing requirements that we've just figured out in the previous step. So that's something else you can do with system simulation. So this is the exact same model, but you can see now the user has converted the engine into a motor battery power plant, and we can build up the complexity of this. This is relatively simple at this stage, but we can start bringing in our motor characteristics. We can start bringing that in and understanding how different characteristics of that motor will affect the performance of the system. And we can also start selecting the battery pack. And again, AimSim and the system simulation tools allow you to do things, quite a lot of things in that space. And then finally, we might come up with a candidate design, and we want to figure out how efficient that is, what its charge behavior would be, will it meet our requirements, and we can look at advanced things like the aging of the battery pack over multiple duty cycles. So just to summarize some of the practical things you could do with a systems model to get you thinking about the possibilities. So we can identify the electrical system requirements. So we saw how in the video you could figure out what the size and power requirements are. We can then use that information to size up the electric motor and battery, and then we can use our systems model to validate those designs and see how what the dynamic characteristics are of the system. But that's part of the picture. We can also then use this effectively a digital twin of our excavator in man in the loop, software in the loop, hardware in the loop, real-time integration. So we can take that model and then either convert it into a real-time model and run it with use it to validate controls, either software controls or hardware controls, or we can put a kind of man in the loop, which is again something Darius is going to cover in subsequent sessions in a lot more detail, and understand how this system's going to perform and how it's going to feel for the operator. So I'm hoping that's given you a little sense of some of the possibilities around system simulation and the AimSim tool. So I'm now going to hand over to Darius to cover, get into the detail of hydrogen fuel cells. So Darius.
Okay, Adam, thank you very much for the introduction. I'm trying to take over the controls.
Yes, let me give you. Okay, you should be good now.
Okay, let's try it.
Okay, so we got the first question here. Darius, do you want me to turn this poll on?
Yes, please.
Okay, just grabbing the. All right, I'll let you introduce it.
So the question is that whether your company is actively looking at zero emission solutions, or whether you are investigating opportunities for deploying this type of solutions into your products. And very simple answers, not yet. And then we split into yes, battery electric, yes, fuel cell electric. So whether you've got pure battery powered solution or you are more towards fuel cell and hydrogen.
Okay, thanks for those who voted. I'll share the results. So we had around 42% of the folks who responded said not yet. So I guess it's something again you might be looking at as you're on this session. And then an interesting mix. So with 33% of the folks who responded battery electric and 25% fuel cell electric. So hopefully you can see that on your screens. I'll hide that again. And then Darius, I think you should have control.
Okay, let's try it. I will just move on.
Yep.
Okay.
Yep.
Okay, I hope it's me changing the slides. Super. So thank you very much for the introduction to Emisim. It's I hope now showing how powerful the tool is. Before I move on to the example of hydrogen fuel cell powered wheel loader, I will give some basic information, background information about fuel cell and hydrogen, why we're talking about this technology now. So first of all, we have to understand what the fuel cell is. And we'll start with a black box. It's a simple approach. As long as we supply hydrogen and oxygen to the black box, to the fuel cell, it will provide electricity. And actually, when you look into fuel cell into more details, you will see that there are three main components, mainly polymer electrolyte membrane or proton exchange membrane, and two electrodes, anode and cathode, similarly to batteries. What is happening here, this is actually an electrochemical device, so there are no moving parts. And as long as we provide those reactants, hydrogen, oxygen, we will get this electric current generated. So how is happening? On the anode side, we've got an electrochemical reaction taking place, which allows for electrons being splitted from a hydrogen molecule. And as the result of that, hydrogen protons are migrating from anode through the electrolyte to the cathode side. And as soon as we connect the external load, electrons will have path to flow through the external circuit and migrate from anode side to cathode side as well. So then on the cathode side, we've got now oxygen coming with air, and electrons coming from external circuit plus hydrogen protons. And another electrochemical reaction takes place here, which combines all of them and creates water. During the operations of a fuel cell, some heat is also generated. So I suppose this is the simplest way to explain about a basic fuel cell operation. And what I would like to highlight also on this slide is that as you see that the current, external current demanded by load is directly linked to the hydrogen and oxygen quantities. So let's keep in mind that the fuel cell will work perhaps in optimum way when the conditions are steady state conditions. So by that I mean that the load is not changing. So let's say you've got fixed current demanded by external load, and for these conditions it's quite easy to maintain the reactions happening and incoming hydrogen and oxygen. So it's very important to keep in mind that steady state conditions are perhaps the most favorable for a fuel cell. One single cell is not really powerful device. In order to meet power requirement, we will be most likely in need to connect multiple cells together. And by doing so, we will end up with a fuel cell stack. So on this slide, I've got a fuel cell stack here, trying to highlight it is my pointer. And as you can see now the fuel cell system is a little bit more complicated than just single cell. And we can distinguish here four main parts of it. So apart from the fuel cell stack, we've got here hydrogen supply subsystem, if you like. Also, we've got on the oxygen side supply, and oxygen comes in most cases from air. So we've got this subsystem here. And also, in order for fuel cell to operate well, you have to maintain the temperature, the thermal management is quite important. And for that reason, we've got here a cooling subsystem or thermal management subsystem, if you like. So I'm not going into details of describing every single component here. I just want to highlight that designing, developing the fuel cell systems is a engineering challenge, is an engineering task on itself. So when you develop this system, you've got challenges, and then when you want to deploy it into application like a bus, car, or any other application, you have to overcome even more challenges. So I'll perhaps come back to this on another slide. Fuel cell idea is not actually a recent new idea. It's almost 200 years since Sir William Grove for the first time advertised or he came up with this idea saying that fuel cell will work. I think it was in 1842 when he actually presented a working fuel cell. And since then, fuel cell technology has been in development, we can call it. And over the years, there were different applications like space shuttles, spaceships, or different projects when they wanted to prove that fuel cell can be deployed to off-highway machinery like a tractor, or then on-road vehicles like passenger cars or vans. So over the years, the development was happening. And over the last decade, I suppose we've seen the most advanced development. Also, it seems that there is now a lot of talk about zero emissions, carbon neutral societies, and many countries now are putting forward roadmaps, legislations, proposals for achieving these targets. And fuel cells and hydrogen are taking, I would call it, a main stage in those proposals and roadmaps. So it seems that the time is all right. And also, if you look into the fuel cell stocks, so on this plot, I put three main players, namely Ballard, Plug Power, and ITM. And as you can see on the x-axis here, we've got about 5-year period. So since end of 2015, let's call it. For the first 4 years of this plot, we see that the stock exchange was relatively, I call it, lazy. So not much excitement there. So investors were not putting money towards hydrogen and fuel cell technology. But if you look at the, really high gradient of the price over last year, it shows that the investments are really happy to put money towards this technology. So taking all the facts into account, I believe that this is now the right time for investigations and pushing towards fuel cell and hydrogen technology. And if you go to off-highway market, it's actually fuel cell is present there already at some part. So if you think about forklifts, which are working in warehouses, there are already around the world about 40,000 forklifts powered by the hydrogen fuel cells powertrains. And on the other picture, you see a container handler or stack rack reacher by Hyster-Yale, and I believe this is getting into commercialization phase soon as well. So you can see that this technology, hydrogen fuel cell, is already migrating into this market. Also, the other examples of highway might be excavators. And you might be aware that JCB last year has shown 20-ton excavator powered by hydrogen fuel cell. And a few years before that, Volvo has shown smaller, about 3-ton machine powered by the fuel cell provided by their partner Symbio from France. And also Hyundai has announced that by 2023, they will offer commercial available heavy equipment powered by hydrogen fuel cells. So it shows that the projects are getting into bigger scale and more complex machinery. And also agriculture and open mining machinery, there are some examples projects already happening there. So as I mentioned, those challenges when you develop the hydrogen and fuel cell system, when you start applying this technology into the off-highway machinery, you're facing even more challenges. So I suppose that the picture here I want to explain is that the duty cycle that is most repeatable or easy to predict, like let's say material handling or warehouse work, when you can almost clearly define during the day what the machine is going to do, is perhaps the first market to target, because it's easy to develop optimized fuel cell system for this application. And then when you go towards more challenging applications like excavator, when you cannot really predict every day what the machine is going to do. One day it might be, one type of duty cycle, trenching, digging. Another type it might be pipe laying, so completely different from power demand and characteristics. You're facing new challenges. So not only mentioning the fuel cell, the hydrogen price and logistics. So if you think about developing machinery powered by hydrogen, you have to take into account now that you are going to use hydrogen, which is much more expensive than diesel fuel, and you cannot get it everywhere. So you have to arrange for logistic and on-site storage, and this creates additional cost headaches for the program managers. And from engineering point of view, perhaps when you work with fuel cell application already in your machinery, your testing routine might be affected by the fact that you're working with hydrogen. You've got limited amount of hydrogen on your machinery. Before you refill the tank, you have to conduct some testing. And then very often, as you know, that when you test any product, you might need to change some components or some software, and this takes time. During this time, when you're actually not operating the machinery, fuel cell temperature will go down. And then if you want to go back to the point when you finish, before you change component or software, you have to perhaps lose some hydrogen or battery power to bring up the temperature of fuel cell. So all those things are making your life a little bit more difficult when you're developing the applications for fuel cell technology. However, it's not all bad news. There are tools and methodologies that are helping with developing such applications. And this is why we are here. So at this point, I will move towards that example. And before I describe the example, I will touch on the software that I'm using. As Adam presented MESIM extensively, I won't focus too much. I'll just say that it's very powerful, in my mind, very powerful multi-domain, multi-physics simulation package. However, over the years, I was always tasked with providing a real-time digital twin that we can actually operate. So I mean that you can have a driver, a human being pulling the joysticks, pressing the pedals and controlling the steering wheel, and then you can deploy simulations to this level. For that reason, we had to link MESIM to different tools, and that is a tool coming from SimCenter, which calls 3D Motion. I'm not expert on this one. I learned about this one a good few years ago, and it wasn't doing what I needed, so I moved towards another thing, which is MEVA simulation software. And briefly about this one, just as an introduction, this software is targeted for digital twin simulators, R&D type of simulators, and it's got all the multi-body dynamics and soil mechanics, so it's got the machine ground interaction simulated very accurately, and it does in real time. And as you can see from this Yin-Yang picture, I tried to picture here that those tools are overlapping on some aspects like hydraulics, drivelines, FMU, FMI, hybrids, and so on. And very balanced use of those two tools can bring you a really even more powerful tool. So you've got now two powerful tools, simulation tools, which you combine together, and as a result of that, you're getting even more powerful combination. And that combination I'm using towards virtual product development. So now I will take you through the steps how to develop a fuel cell powered wheel loader from the scratch, if you like. So the whole story starts before even you've got any CAD design done. So we decided that this is a wheeled machine that has got a bucket in front, and we want to move, let's say, a specific payload from specific place A to B at specific time. And what we do, so we use at this point, at this phase of the project, MEVA simulation, which is coming also with a simulator. You have to have this human machine interface. It can be very advanced simulator, 6 degrees of freedom, virtual reality, or curate screens, or it can be very simple setup like on desk that when you've got pedals, joysticks, and steering wheel. So it's up to you what you want to have. But anyway, we're giving this to the operator, and we task him to drive this machine. So it's virtual machine. He is operating a duty cycle that we task him with. And for example, it can be short loading cycle when you ask him to go into the pile, grab, let's say, as much as he can of the stones and dump them into the skip and repeat it. So at this stage, we do not simulate any hydraulics, any drive lines, any power plant, either engine or fuel cell. We just basically wheels and actuators. And we make control of the wheels dependent on the pedal positions, and actuators, we control them from the joystick position. So we scale joystick, let's say, into the actuator velocity, and then operators got way of controlling. So if he pushes joystick farther, the actuator moves faster and so on. And then by performing a duty cycle, he has to focus on controlling the machine in the right way, if you like. So he cannot go very quickly into the pipe because it will make the machine unstable. He just consciously operates the machine. And as the results of this phase, we're getting data. So you've got virtual representation of the first cut of the machine, if you like. And what you're getting is actual data for the torque, speed of the wheels, and velocity, position, and force of the actuators. So just thinking about the project advance, like, so normally to get this type of data, you have to instrument a machine and put it into the proving ground, test it, and get the data there, or you have to use some other scaling down from existing product if you got some data. So what we're seeing here is a massive advantage of getting actual data at very early at the phase earlier of the project. And what do we do with this data? So we move on to MESIM, and now we use the torque speed information from the simulator to design driver, and we design it from the wheel. So if you know that you've got, let's say, 4 wheels, and then you want to have a type of 4-wheel drive or transmission, whether it's mechanical transmission or hydrostatic transmission, you do build a lot of MESIM configurations, as many as you like, as you need, and you benchmark them against themselves, each other in MESIM. So you've got, as Adam showed, your ways of comparing different configurations, changing parameters, and different layout as well. So on this picture, you can see that it's hydrostatic transmission versus kind of parallel hybrid engine and electric motor. But at the end of the day, what you're getting here is a good understanding of the driveline performance based on the duty cycle that is actual duty cycle you need to meet. So if we have to pick up the electric motor characteristics or battery characteristics, we do it right. We do select it for the duty cycle that it has to be met in real life. And similarly, we do with hydraulics. So when you've got now actuator, force, displacement, and position, velocity, position, and force, you can pick up a hydraulic ram size, i.e. piston diameter and rod diameter, and from that you will get the pressure and flow required by this single cylinder. If you do it for all the services, all the actuators within your machine, you will get hydraulic flow demanded by the combined services. And then you can decide whether you do meet this flow from a single pump or multi-pump solutions, what do you put between the pump and the actuators? It's again up to you. You can go for different type of hydraulic circuits. On those two pictures, I tried to put two different solutions. So one is independent metering valve configuration, when you've got 4 valves. It's actually electrohydraulic configuration. You've got 4 valves making up for a service control of the single service, and those valves are controlled from the ECU, so electronic control unit send signals for the control operations. On the other picture, we've got actually fixed, if you like, a spool type of valve. So the geometry is fixed by the design, and MESIM can also take you down to the level when you design this geometry. So 2 ways you can approach simulations. You can take data existing from existing components, from your suppliers, from websites, wherever you can get them. You can implement them to simulation, and you can see how the machine performs, whether it meets your requirements. Or you can give yourself freedom, and you can design the valve. So you can use hydraulics component design features in MESIM, and you can come up with a valve you would like to have. You can go then to hydraulic supplier and explain, this is what I want because it was in my simulation, and can you get something like that. So, and then you start your iterations with the supplier, saying what is the closest match for the solution. And again, you can compare all that power, pressure, flow within both or even more circuits. So it's giving you that advantage of multiple what-if scenarios, testing different solutions without any physical prototype, without any physical components being fitted to the machine and machine being sent to the proving ground. So it's again helping and accelerating the whole machine development process. And now we're moving to fuel cells. So when you've got driveline and you've got hydraulics, in the case of wheel loader, it's perhaps 2 main systems that demanding the power. You can, from those 2 separate simulations, generate the information about power demand, and then you can move on to the fuel cell. So, and again, MESIM is a very great flexible platform simulation tool, because this now, when it comes to fuel cells, allows you to develop your single cell. So almost from the geometry of the membrane and the cathodes and the size of the fuel cell, one single cell, it will provide you the polarization curve. That curve shown here on the graph is on the x-axis, we've got the current density of the cell. So it's current generated by the cell divided by the area, and then the voltage provided by the cell. It's very crucial information. It's a very important one, because based on this information, then we build a fuel cell stack, and we have to decide on the voltage that fuel cell system has to provide, the current, so we will dictate how many fuel cells, what size of the fuel cell is, and so on. And at the same time, we have to then design around this fuel cell stack hydrogen supply, oxygen supply, and thermal system, as you remember from the few slides before. And again, MESIM is allowing you to do it in one tool. You don't have to go to multiple tools and develop it. So from the driveline and hydraulics simulations systems, you've got the load. Now we're putting this load for the fuel cell system. And as you can see on this picture, I'll try to highlight it again. We've got here fuel cell stack and also battery. So it's most likely that in any way you will end up with having fuel cell and a battery. If you remember when I talked about this duty cycle for current demand from fuel cell, you would like to work at steady state conditions. So ideally, any other peaks and positive peaks and negative peaks from the current steady state current, you should be too accommodated by battery. So when you've got, let's say, regenerative braking, or you lower load on the bucket, this energy has to go to battery. There is no way that fuel cell will regenerate that battery and use it. So you have to have this battery there. And again, it's taking your decisions, sizing of the system, and understanding, predicting the performance ahead of any prototype is built. So especially when you talk about fuel cells, it's much more expensive than building, let's say, diesel engine or another configuration. So it will allow you to understand whether you're going right way. So something on something that Adam already mentioned is control development. So how MEC can help in this way, in these activities. So first of all, I have to mention that there is some feature in MEC, which you can see here. There are blocks called state charts. So you can develop your basic logic in MEC. You don't have to go to third-party tool. If you have to go to another tool to develop really complex and advanced logic, you can do it in different ways. So one way is perhaps exporting MEC model as FMU, or if you're using MATLAB Simulink, as I used in past, is a dedicated interface for MATLAB Simulink. So you can go either way. Actually, there are 3 ways. So you can have MEC model exported to Simulink as function, and you can work around this in Simulink only. You can export Simulink model to MEC, so you import it and you've got export some parameters, and you then change perhaps more in MEC than in the controller. And the third way is when you actually run co-simulation, so perhaps the most flexible one, because 2 solvers are running their own tool and you've got access to both tools at the same time, so you can change parameters of both sides and you can change layout of both sides. So this is another way, and this takes your control engineers, it allows them to be involved in the system design early in the project as well. So by providing them with a plant model, let's say it's a whole vehicle, whole wheel loader, a plant model, they can start developing the control strategy for fuel cell, for BMS, battery management system, or for the electrohydraulics for the valves. So anything that has to be controlled, they've got there now a plant model representing accurately the machine they will have at some point available to them, but they can start their process very early. And from model software in the loop, they can go to hardware loop. So when MEC runs in real time, they can validate and verify the code by running hardware in the loop test. So this is a massive step towards the validated code that you've got in your hand, safe algorithm that is all right to put, it's safe to put on the machine. And now, what Adam also mentioned is driver in the loop. So naturally, when you progress, when you follow those steps, you end up ending up with something which is digital twin of your product, which you will prototype at some phase. But now you can go back to the simulator again. So from all those simulations, you selected the configurations that you want to use, and you giving up now this virtual representation of the machine again to the operator. So whereas previously he had no hydraulics, no driveline, no fuel cell information there, it just was him controlling wheels and actuators. Now the whole design is in his hands. So he can advise whether flow share is right, whether what happens when he puts the gear in reverse and apply full hydraulics, whether the power demand is met by the system, or is it too slow on the hydraulics, or is it too slow on the driveline, and so on. So he can now provide you a very good and valid feedback. So again, if you think about, you haven't manufactured anything yet, you've just done extensively simulations of all crucial aspects, everything that matters to the machine design, and operator can test it for you. So you don't have to wait for he doesn't have to wait, she doesn't have to wait for the machine being available. He jumps on the simulator, drives it in the way normally he would drive a machine, and you're getting his feedback. Not only his feedback, but also you're getting a lot of information. So you can imagine, as those plots are showing here, fuel cell as temperature, battery stage of charge, and hydrogen use. You can also get any information from the simulation. So it's like instrumenting your machine so extensively that you can measure anything you like. So every single component is in the simulation environment is bringing the information about power, flow, speed, pressure, whatever you call it. It's there, so you have to just grab it and investigate whether it meets your requirements. So this is very powerful, and it brings all the answers to you early in the design phase. Something which is perhaps less common, actually I'm not sure if anyone is using this approach, is a follow-up from the previous step. When you've got the operator in the loop with the virtual representation of the machine, why not to swap the virtual representation of the fuel cell system with a real one? So if you imagine that you've got the fuel cell and electric motor and hydrogen storage or whatever is required for the fuel cell system connected on the test rig. That test rig is then hooked up to a virtual representation of the machine in the form of a simulator. So the operator can demand the motor speed. Let's say if the application is one motor speed, one electric motor powering both driveline and the shaft through the transmission is going to the hydraulic pump. You can imagine that he demands the electric motor speed, then demand is sent to the test rig, motor speed is set up, and the current is taken from the actual fuel cell / battery, and the actual hydrogen is used. And in return, this test rig is sending the actual motor speed to the simulator. And as soon as the operator starts performing duty cycle, he engages, forward, or he applies load to hydraulics. Then we see that the load generated in virtual environment is really transferred to test rig as a load on the electric motor. So it's demand on the electric brake for the electric motor to apply the torque to electric motor. And this way you merge two environments, real and virtual. So you can test your virtual machine in the lab environment when you don't have to worry about hydrogen logistics. Perhaps you can get cheaper hydrogen if you generate it on site from the renewable power and so on. You don't have to order it from expensive places. So anyway, this is taking your development phase to the next level. So you accurately, if you have to swap something on the fuel cell system, you can do it in here, and you can accurately map the configuration, calibration of the fuel cell system to the application, in this case, wheel loader shovel. And I think from this, you could simply see that this approach is building or is actually creating a silo breaker. This allows for multi-domain subject matter experts to collaborate, to be exposed to the same things at the same time, rather than in sequential approach when you got hydraulics working separately from other teams and so on. So it's taking all that knowledge you've got in your company and making use of it. And also something which I haven't mentioned is perhaps structures, that once you've got that CAD geometry done and you've got forces coming from the simulator, you can put this to stress engineers for them to run FEA analysis on the design of the loader arm. And if you find that it's not the optimal one, you want to change, you can change it in the simulation far quicker than on the actual machine. So a true silo breaker. And also, okay, let's sum up. So if you now seen those steps, and you can clearly see that you have got now solution that is optimized, and you can engage operator, you can get assessment of the machine without any prototype available to you, is great advantage. So you've got all the engineering teams working on their bits, bringing them together and validating the same machine. However, by doing this, you end up with a digital twin that engineering life perhaps might come to, let's say, end. You don't need to do much more engineering wise when you're happy with the design. But on the other hand, you can use this digital twin for other aspects. So it's, let's say, free of charge because it's now sitting in your lab, it's there. You can start doing some predictive maintenance. You can do other clever stuff with this simulator. But also you can promote your product. So let's say if you're working on the new machine that is not manufactured yet, you can deploy, you can use this simulator, you can give it to your customers, you can invite people to assess the machine, and maybe perhaps some of them will come up with some ideas like, why don't do this and that before you manufacture a prototype. So the benefits of doing this process are not just purely engineering, they are reaching far and away for other activities as well. So I think with this one, it's going back to Adam.
Thank you very much, Darius. I'll let you talk there because it was really interesting. Just to remind folks, we don't have long left, but if you do have any questions on what you've just seen, feel free to post them. We've got sort of 5 minutes now. We can take a few questions. And sort of just as a sort of final bit of the presentation, I'm just going to share, I think, one more slide. It's a bit wordy, but I think you've probably seen quite a lot in this session. And we wondered if we could distill it down into sort of how do you start on this journey. So if this is something that kind of you are looking at as a company or as an individual to start building up a digital twin model, something like we've just seen today, we sort of broke it down a little bit more into kind of more bite-sized steps here. So really looking at the first step here in the process, which is it is the kind of component or system simulations that I sort of started the story with at the beginning of the presentation. And that's where you kind of start with this. And hopefully you've picked up that you don't have to have all the CAD or all the design information to get going on this. You can start sizing designs quite quickly with past information, with text, data sheets, etc. And then you can build from there. And then hopefully you again have got a sense of once you've built these up, you can then start adding building up the system, and then you can start using that for control validation. Some of the cool stuff that Darius has just showed about operator validation, moving towards a full virtual twin. And we've highlighted some of the things that you can do. You know, you get some benefits straight away. You get an idea of the performance of the system initially, and of the components and the system. And I just said, if you do want to find out more, obviously email myself or Darius. We're more than happy to talk a little bit more and go into more detail of what we shared. James, I don't know if we've got any questions that have come in just for the last couple of minutes.
Yeah, we've got a few. So first up, does linking the tools such as AIMSIM and FMUs require any coding?
Darius, do you want to take that one?
Okay, so I will take this one. No, actually, not from the user point of view, if you like. So I'm user and I'm using the features that are built into MESIM, and in this case in Meva as well. So it's just creating an interface block in the sketch of MESIM, and on the other side, linking it to Meva is easy as well. So the coding has been done by the software suppliers. So they had to code something, but I'm not exposed to this coding, so I'm just using a graphical user interface.
Thanks. James, any others there?
Yeah, we got one here from David O'Callaghan. Could this system work with a hybrid system using an IC engine? Plus, would this work with other equipment?
So can I take this one?
Yes,
I see these
definitely.
questions here. Yeah, super. Because actually, I forgot to mention this perfect question. Thank you for that. This methodology is very generic. So the example is wheel loader fuel cell, but it can be deployed, used for any type of machinery. It doesn't have to be wheel loader. It can be not even off highway, or let's say it can be port crane or tractor or whatever. So whatever you can simulate, it can do. So I won't perhaps claim that it can do, I don't know, yeah, it can do everything, perhaps not marine stuff, yeah. And that engine hybrid configuration is perhaps the best one, because when you put the electric motor on the engine and you've got the testing anyway, why not to use this dynamometer for linking to the simulator digital twin of your application, whether it's of highway machinery, track, whatever. So yeah, it is very generic. It's just an example which is shown here.
James, any others? I think we've still got a minute or so.
Yeah, we've got another question here from Nathaniel Tan. Will there be more of these kind of webinars for other applications like buses or automotive? And will there be any deep dives into those areas?
Yeah, we're always looking for topics that people are interested in, so we will take that feedback, and potentially, yes, we do have some examples are similar with electric buses that might have been involved in. So yeah, that would be a possibility. So watch this space.
Okay, brilliant. We've got another question here. Can we get a free trial of AimSim?
Yes, generally speaking. What normally happens actually is that we would have a get together if you're interested in finding out more, and then a bit of conversation, see if it fits the bill, see what you need, and then typically, yes, we often do some what we call an evaluation process, and that could involve setting up some of the software. We work with you. Obviously these days it's all remote via web, but yeah, follow up with us if that's something you're interested in. We can dig into that a lot more and get the ball rolling. James, I think we've run out of time. It's 4 o'clock. So thank you everyone for attending. I hope it's been useful. You'll get a feedback questionnaire, I believe. If you can fill it out, we'd love to hear your feedback. But again, thanks for attending, and I'll say goodbye there. And thank you very much, Darius, for your presentation.
Thank you very much, everyone.
All right.
Thank you.
Bye-bye.
Bye.